I thought I will first give a very quick overview of my research activity and then focus on a particular setting that we have done work with collaborators. As briefly said, my work involves research on penalized likelihood methods for learning and inference. And this is combined with computing and algorithms for complex regression models. We are focusing on regression models. I have done some work on methods for clustering. And then I also focus on certain data analytic settings and software development, particularly statistical software development. So for today, what I'm going to do, I'm going to go bottom up to that list and skip the methods of clustering because it takes a long time. So I will say some things about software development, data analytic settings, and then I will focus a bit more on computing and penalized likelihoods with a small data analytic setting. So I believe that data scientists generally should really develop their own software, especially if they are in the methods development business. It's good for reproducibility, replicability, if you are involved in experiments that need to be replicable. And also it's very good for more selfish goals like citations and promoting your research. And also it's really good for aiding discovery. So if you develop something and you implement it, then someone else or even yourself can take it and advance it to the next level. So I use like these values in my research, and I try to spend some time developing software on all the methods I develop. So there are some model-specific and penalized likelihood-specific software packages here, like brglm, betareg, brs. Then there are some data-analytic software specific to certain application areas, like Tracker, which has to do with running and cycling data from GPS-enabled devices. And then there are some more geeky tools, like enrich with, which allows you to take pure R objects and enrich them with components that they are not in there. So I really like that. I'm currently working quite intensively on that. So here, for example, I'm enriching a family object, a binomial object, with derivatives of the finance function, which are not available in the core distribution. So I really like that. I also focus on data analytic settings. My current focus is mainly on sports and health, and broadly in modeling fitness activity and sport activity combined with human behavior to see how these impact health and well-being in general. So here, for example, I have like some data as being prepared using the Tracker package I told you about earlier. And this is like a modeling setting which we are faced with quite a lot in some of the work we are doing with elite sports, where you have the physiology and the psychology of the athlete affecting their fitness. And the psychology and physiology are also affected by the training they do, right? And you want to say something about how physiology and psychology affect fitness or are associated with fitness without having to specify distribution for everything, right? You don't really want to be very specific on how physiology and psychology interact for this. You just want to focus on the relationship. So you want to partially specify a model, but still get what you are after, right? So we are working in this area. It's a pretty challenging area, both in the data perspective. You have to handle missingness. You have to handle time dependence. You have to handle very complex dependencies between the various proxies of physiology, psychology, and so on and so forth, and come up to a conclusion somehow. And also you have heterogeneity, because usually you get measurements over many individuals about the same effect. So you have to somehow pull all this information together. Another area that I'm interested in is natural hazards, and particularly on quantifying risk from post-hazard survey data. So this picture is from an earthquake, and the points are buildings, and the contours are the ground acceleration caused by the earthquake. And you're trying to measure the damage on the buildings and explain it using characteristics of the hazard itself. Of course, a lot of challenges there as well. For example, sampling is biased. Usually the survey teams, they only survey buildings that are heavily damaged. So you have to take all this into account when you do the modeling. And then I do some applications in finance. I didn't have a nice picture to show there. I think they have pretty boring pictures generally. So it's dynamics of financial indicators with structural dependencies that we care about, like yield curve modeling and stuff like this. Sorry. So on the more theory and methodology part of myself, I usually work on methods and theory that strive to improve estimation and enhance inferential procedures. And usually this involves penalizing the likelihood or likelihood quantities somehow, so that you get improved estimates or improved properties from the inferential procedures you have. We focus quite a lot on complex models, particularly models with intractable likelihoods, both in terms of computation and analytically intractable sometimes. So how do you correct inference in those settings when even the maximum likelihood estimation framework is not available? And also we take particular care on making all these scalable, both in terms of sample size and number of variables. We focus quite a lot on particular modeling frameworks, particularly on ordinal and nominal categorical responses, generalized linear mixed effects models, where you have a clustering of the observations usually, item response theory models, which is a very nice inferential framework for inferring abilities and difficulties of items in tests, and beta-regression, which is pretty particular in proportion modeling. So now I'm going to focus a bit more on a very special linear mixed model, which usually involves very small data. So this is meta-analysis and meta-regression. So it's a pretty simple setting. Actually, it's deceivingly simple. You have data from k-independent studies on a common effect of interest, usually scattered around the literature, and someone has done some systematic review and recorded the summary and the estimated summary variance. They might have used some delta method to bring all the variances on the same scale, but that's the setting. And then you have some study-specific explanatory variables that come with this paper. And the aim is to synthesize the evidence about the common effect of interest, taking into account the estimation variances recorded, and also to account for and quantify heterogeneity across studies. So all these studies are independent, and they might lead to slightly different results, so you somehow have to pull them together. Now, this is a quite traditional setting where you have small to moderate at best sized data sets, and they are usually very hard to collect. So someone has to sit down, usually for years, to do systematic reviews and analyze what its paper had done and how the experiments carried out. One example of that is the meat consumption data. So the good thing with meta-analysis is that these things usually make headlines very quickly. So for example, here, you might be familiar with the headline, is meat killing us? Is eating processed meat better than eating unprocessed meat? And so on and so forth. And this is a data set which has been used to one of the studies that led to this stream of press. So here you have meat consumption and relative risk, the log relative risk of all-cause mortality, from 8 prospective studies about consumption of unprocessed red meat and 8 about unprocessed red meat. The relative risks are relative in the sense that you measure the risk of a high consumption versus a low consumption group for every type of meat. And you collect all this data from systematic reviews. These are given in this paper in the footnote. And then you want to say something about the difference in relative risk between processed and non-processed meat. The working model that is usually used for that is a very simple random effects model, where you assume that the summaries are independent, conditionally on some independent random effects UI. And then the conditional distribution of the summaries given the random effects is normal with mean with this very simple regression structure here with a random intercept. And then the variance of that normal is set to the estimation variance you had for the summary. Right? It's a pretty unrealistic model. However, it works quite well, as we will see later. Random effects meta-analysis results when all the covariates are 1. So in that case, you're simply interested on the size of the effects from the summaries. What I'm going to do here, I'm going to denote X to be the model matrix with rows x1 to xn. Sigma hat will be the diagonal matrix with the summary variance on the diagonal, and W will be the inverse of the marginal variance-covariance matrix for Y's. This parameter psi is what is called heterogeneity parameter. So they are trying to capture how heterogeneous the study is and control for that heterogeneity before saying something about beta. Estimation for beta, if psi was fixed, is usually done by weighted least squares. So if you fix psi, this is a weighted least squares problem. You simply weight by the matrix W, the inverse of the marginal variance, and you get a weighted least squares estimator. And then you have to estimate psi, of course, in order for all this to work. You can use the maximum likelihood estimator of psi, which results as the solution of a simple nonlinear estimating equation here. R is the residuals. And an alternative and classical estimator for psi is the Desimonian and Laird estimator, where they use moments and the concurrence statistic in this particular way to get an estimator of psi. So both of these are used in the literature with a preference on the Desimonian and Laird. So let's go back to the mid-consumption data. Here's the estimate for the log relative risk in terms of type. And here I report some estimates. I mean, there's nothing interesting in that in these figures. The estimates are pretty close to each other. What is interesting is the p-values you get when you test for higher risk associated for the consumption of processed meat. So what you see here is that Desimonian and Laird, by a simple wall test here, leads to a p-value of 0.003, and then you get a slightly larger p-value using the likelihood ratio test. And this has been interpreted as weak evidence that processed red meat is actually worse in terms of relative risk of all-cause mortality than unprocessed meat. They are both bad, but which is worse was the question here. Once you delve a bit deeper into the model and you do a small simulation study, you immediately notice that the maximum likelihood estimator is biased. So this dark gray line is the mean, is downwards biased, and the Desimonian Laird is a bit less biased, but it has terrible efficiency properties. So it has massive variance compared to the maximum likelihood estimator. And now downwards bias in this framework is very dangerous. The reason is that if you underestimate psi, the heterogeneity parameter, essentially you are overestimating the information you have about your parameters. Because the information is inversely proportional to psi. And if you overestimate the information, you will be underestimating the standard errors for the parameters, which means that you will lead, you have the potential to result in very strong conclusions about your outcome. And of course, the low efficiency of psi hat Desimonian Laird impacts inference as well. So what can we do about that? One way is to try to reduce bias, and this is something that I've been working for several years now. This is a very general bird's eye view of bias reduction methods. So the task is pretty simple. You have a bias estimator theta hat, and you want to correct for that bias. If you knew the bias function and the true value, you would simply take it off from the original estimator. But you usually don't know the bias function, and typically you don't know the true parameter value, right? Otherwise, there's no point of this discussion. And there are two kinds of methods. This comes from a review paper that I wrote. There are explicit methods where you simply estimate the bias and then you take it off the estimator, like the bootstrap, jackknife, asymptotic bias corrections, and others. And there are implicit methods where you simply estimate the function. You don't estimate the parameter as well. And then you solve an implicit equation on the new estimator, right? And you have indirect inference there, which is pretty popular in econometrics. And you also get an adjusted score equations method that I will show you later. So this kind of puts everything under the same umbrella, and also leads to very neat algorithms if you want to reduce bias. So here is an update which pretty much results to all the estimators I spoke about earlier. The idea is that you start at a point here, the maximum likelihood estimate, and you try to make a step in the direction of steepest descent of the score function. Here, of course, the score function is 0, but once you make this step, you also correct for the bias at this step. So here the bias is negative, so you go on the left, and then you try to go again to the direction of the MLE, which is here, right? But before doing that, you correct for the bias. And so you take a smaller step, and you do that iteratively. So the quantities involved are pretty simple. So basically, you have the information matrix. Here I have the expected information matrix, but it can also be the observed information if you like. And you also have the bias function involved there, or an approximation of it. And I shouldn't say learning schedule. This is from another talk on stochastic gradient descent. I should say determine the step size there. Sorry. So depending on the approximation you are going to use for the bias, you get all the different methods in a different number of steps. So if you do a single step starting from the MLE and you use the first term in the asymptotic expansion of the bias, you get asymptotic bias correction. So simply you evaluate the first order bias term at the MLE and you take it off the MLE and you get a bias correct estimator. This has been proven it has lower order bias than the MLE. If you approximate the bias, you can get bootstrap with one step. If you iterate to infinity with the approximate bias, you get this adjusted scores approach that I will show you later in the meta-analytic context. And if you iterate with an estimator of the function, you get what we call iterated bootstrap with likelihood adjustment. This is current work with one of my PhD students, Ms. Sofia Kyriakou, and it's pretty good for complex models, especially when you don't have a tractable likelihood. You can use that to carry out bias corrections. So let's focus on the adjusted scores for a sec. So the bias, the first order bias term of the MLE in meta-regression is 0 for the regression parameters. And it's something always negative for the dispersion, for the heterogeneity parameter, which means that you would expect this downwards bias always that we saw in the simulation study. H is simply the hat matrix in that case. And if you plug everything in and do some algebra, you see that the bias-reducing adjusted score equations have a very simple form. The score equations for beta, for the effects, is exactly the same as maximum likelihood. The score equations for psi, the heterogeneity parameter, are a modified version of the maximum likelihood equations, where you have this extra term here, this projection matrix here, I minus h multiplied by w. Now, the integral of the adjusted score functions here is path independent. So there is a penalized likelihood, and actually you can find it. It looks like this. So you penalize the likelihood by the inverse of the Jeffreys prior. And this is exactly equivalent to the adjusted scores. The maximization of this adjusted likelihood is equivalent to solving the adjusted score equations. There are some very neat correspondences between bias reduction and other methods out there. So basically here we reproduce REML if you plug in beta hat psi instead of beta. And also you get a celebrated method, the approximate conditional likelihood of Cox and Reed for inference about psi if you treat the main effects as nuisance. we presented the general bias reduction framework very quickly. And here we apply to meta-analysis and meta-regression. What we have is the first terming the bias expansion of the maximum likelihood estimator, having zero bias for the main effects parameters, sorry, and having bias that is always negative for the heterogeneity parameter, which explains the downwards bias we saw in the illustration earlier. H is just the hat matrix here. By using that and some calculation, we can derive the bias using adjusted score equations, whose solution has second order bias. The equations on the betas are exactly the same as the MLE, so they are unaffected by bias reduction. The equations for the heterogeneity parameter, they are just amended by an extra term here, which will correct for bias. So I need the pointer, right. The integrals of the adjusted score functions are path independent, and actually it's very easy to integrate them, and you end up with an equivalent of maximizing a penalized likelihood, where the penalty is the inverse of the Jeffreys prior. Now, this is quite fruitful because it has correspondences with well-known methods in linear mixed effects models, including restricted maximum likelihood, REML, and also approximate conditional likelihood for inference about psi by Cox and Reed. If you want to maximize this penalized likelihood, you can develop something that is like a coordinate ascent. So first, you update your weights, which is the inverse of the marginal variances. Then you update the values for the betas. And then based on the updated values for the betas, you calculate the current residuals in step 3. And then you use these current residuals to solve a nonlinear equation on the heterogeneity parameter. This is an equation on a single parameter, so it's kind of really easy to solve it really quick. And then you iterate. Usually you don't need more than 5, 10 iterations to converge if you start at the MLE. Here are the same table I showed earlier, just augmented with the maximum penalized likelihood estimates here. What you can note is that the difference in estimates is not that large. Perhaps you have a percentage increase on the heterogeneity parameter. What is notable is that this percentage increase in the heterogeneity estimate causes an inflation on the estimate standard error. So we would expect that p-values based on the new estimates to be slightly larger than they are when we haven't corrected for bias. So just the same simulation study as before, again augmented with the maximum penalized likelihood estimator. So the maximum penalized likelihood estimator is a good compromise here between the bias of the maximum likelihood estimator and the loss of efficiency of the decimonial Laird estimator. So it almost fully compensates for the bias and has good efficiency properties at the same time. If you want to do inference, so if you want to do hypothesis tests, as the test we saw earlier about the processed meat being worse for you than the unprocessed meat, usually you are interested in testing for a specific value of a subset of the main effects, gamma here. And if you take the meta-regression model being correct or adequate, then both the log likelihood ratio and the log penalized likelihood ratio, they have exactly the same asymptotic distribution. So they have chi-squared with degrees of freedom in the dimension of gamma. However, for finite samples, there is a crucial difference, which we kind of saw earlier in the estimates. We expect the penalized likelihood to have a larger curvature than the unpenalized likelihood, which will lead in turn to longer confidence intervals and hence higher p-values. Here is some simulation studies to see how this, because we are basing inference on an asymptotic result, we have to test it in a finite sample regime. So here are some simulation results from the paper we have as a preprint. The left side is coverage probability of 95% confidence intervals based on various methods, including the decimonial layered confidence intervals, likelihood ratio, penalized likelihood ratio, and Skovgard, which is a higher order corrective method based on a modified statistic of the log likelihood ratio. And what you see is that the dark line is the penalized likelihood ratio. What you see is that you get pretty good coverage properties under the same model. Of course, this is a working model, and we had to test also under different sampling schemes which deviate from that model. Here is the results for standardized mean differences from two-arm studies, which is a particularly bad setting because the variance, the estimate of the variance of the summary statistic involves the summary statistic squared. So basically fixing the error in the normals to the variances, you would expect that you would see some loss of performance here. So the penalized likelihood ratio statistic does very well also in that setting. So going back to the case study, if we repeat the test for a high risk associated with the consumption of processed meat using the penalized likelihood ratio statistic, you get an about 2.5 times increase in p-value from what the likelihood ratio gave. So the evidence are actually much weaker than the authors claimed initially. And the results agree with what Skovgard gives. If you want to see details, derivations, demonstrations, comparisons with alternative and other case studies and code, take a look at the preprint of our paper here with Cristiano Varin and Anna Maria Gollo from University of Venice and University of Padova, respectively. Right, so yeah, if anything caught your eye in this presentation, then feel free to talk to me. I'm in the Turing most Thursdays, and you can also check the doodle poll that we all had to complete about our availability. That's my website, and that's my email. And this is a list of references for whatever it's worth. So thank you very much.